Hello everyone. Okay, so let's solve several problems from mixing problems. Okay, so I'm going to do the question 2, 3 and 4 in the handout. So question 2, a tank contains 200 liters of fluid in which 30 grams of salt is dissolved. So what does that mean? Well, 200 liters means that's the amount of fluid, right? So that's liters, that's the volume, right? So volume is actually 200 liters. We need volume to find the concentration, right? So that's important. In which 30 grams of salt is dissolved. So initially you have 30 grams of salt in the tank, right? So that's the initial amount of salt. Okay, so 30 grams. And then let's continue. Brine contains 1 gram of salt per liter is then pumped into the tank at a rate of 4 liters per minute. Okay, so to set up the differential equation, its rate of change of amount of salt with respect to time, dA over dt. So we need the inflow information. So inflow information minus the outflow information, right? So in the inflow, what's the concentration of salt in the inflow? So let's see. Brine contains 1 gram of salt per liter is pumped into the tank. So units are very important. So 1 gram per liter. What's that? That's concentration, right? Gram amount over volume. So that's the inflow concentration of salt times the rate. So pumped into the tank at a rate of 4 liters per minute. So 4 liters per minute, that's the rate. So this is the inflow information. Let me take it back. So concentration of the inflow times the rate of inflow. So as you can see, the liters cancel out. So the units are gram over minutes. So on the left hand side, it's gram over minutes also. So we match with the units. Now the outflow. So really in the outflow we don't know the concentration because it's changing. The amount of salt is changing, right? Already changed when we are pumping water out. So the amount of salt we don't know, that's A. Now you have to make it concentration. So you divide by the volume 200. So this is gram over liter times the rate is, what's the rate that it's going out? So pumped out at the same rate. So rate is 4 liters per minute. So it's 4 liters per minute. And as you can see, liter cancel out, you get gram over minutes. We are good with the units. So let's write down the differential equation. dA over dt is equal to, so 1 times 4 minus 4 times A over 200, right? So we can simplify this little bit. So this is 4 minus 4 and 200 cancel out. So it's A over what? 50. Great. So let's write it again. Right here, dA over dt is actually 4 minus A over 50. That's the differential equation. And the initial condition is, initially you have 30 salt, 30 kilogram or gram of salt. Now let's solve this differential equation. So as I promised in the previous video, I will solve this differential equation using separation of variables. Okay, because in the previous video I solved it using integrating factor method. So to use separation of variables, we have to make the common denominator here. So let's multiply 4 by 50 and divide by 50. So it's going to be 4 times 50, 200 over 50 minus A over 50. So it's really dA over dt, 200 minus A over 50. So that's the differential equation. Now you can separate the variables. dA over, you can take 200 minus A to the left. You have to take 200 also because it's bonded with A, okay? And you can leave 50 here. So 1 over 50, you can take dt to the right. Now what you do is you integrate both sides. So if you integrate the right hand side, it's easy. It's t over 50, right? If you integrate 1, you get t and plus c, of course. And then on the left hand side, if you integrate this, so here's the rule. If you integrate 1 over ax plus b, what you're going to get is natural log absolute value of ax plus b divide by a. So you have to divide by the coefficient of a. So it's going to be natural log absolute value 200 minus a divide by what? -1, because the coefficient of a is -1. You do not divide by 200, right? That's the constant term. You divide by the coefficient of a. All right, anyways, let's take this negative to the right. So it's natural log 200 minus a. So if you multiply by negative, so it's negative t over 50. Negative c is plus c. C is an arbitrary constant. That's fine. Okay, let's make some space. Okay, now we want to make a subject. So let's take the e of the left hand side to get rid of e of the right hand side to get rid of ln on the left hand side. So it's 200 minus a. It's e to the negative t over 50 plus c. Now to make a subject, what can we do? We can take a to the right, this guy to the left. So it's 200 minus e to the negative t over 50 plus c is equal to a. So let's rewrite this. A is actually 200 minus e to the negative t over 50 plus c. So a is 200 minus, we can split this e to the plus c, it's going to be e to the c times e to the negative t over 50. E to the c is an arbitrary constant, so we can write it as what? C again, c e to the negative 50, c e to the negative t over 50. This is the solution. Only thing that we need to do now is to use the initial condition. So initially you have 30 grams of salt, right? So let's use that. So when t is equal to 0, a is 30. So 30 is equal to 200 minus c, e to the 0 is 1, right? So 30 is equal to 200 minus c. So c is going to be what? 170? Yes. C is 170. So let's replace c by the appropriate value. A is 200 minus 170 e to the negative t over 50. This is the solution of the differential equation. Okay, so that's how you solve the second problem in the handout. All right then, so let's solve question 4 in the handout, because question 4 is little bit different. Let's read it. So a tank with 200 meter cube water. So what's that 200 meter cube? That's the volume, right? Because look at the units. That's 200 meter cube volume, and that's the amount of water that you have in the tank, which contains 10 grams of pollute substance. So 10 grams of pollute substance is present in the tank right now. So that's the initial amount of salt that you have in the tank. So that's the initial condition. Great. Now let's set up the differential equation. dE over dt is actually inflow minus the outflow, right? Information about inflow minus outflow. So information about inflow, you need concentration times the inflow rate. So let's look at the concentration. Initially, pure water is poured into the tank at a rate of 5 meter cube per second. Now don't get mixed up with the initially word. That's not the initial condition. So basically what this saying is that you are pumping pure water into the tank. So how much salt is coming into the tank, or pollute substance coming into the tank? There's no pollute substance coming into the tank, right? Because you're pumping pure water. So concentration of pollutant in the inflow is really 0, because there's no pollutant in the inflow, right? So that's 0 times the rate that comes in. I mean, it even doesn't matter, because 0 times anything is 0, right? So inflow is actually 0. Understand that, okay? Because there's no pollutant coming into the tank. Alright, even though there's no pollutant coming into the tank, outflow is still important, because you still have pollute substance in the tank, right? So it's going to go out, but we don't know how much gonna go out, or we don't know how it's changing, right? So because the pollute substance is changing, so the concentration in the outflow is, we don't know the amount. To make it concentration, you divide by 200, right? To make it concentration, you multiply by the rate. So the rate that goes out is 5 meter cube per second. So that's the rate that goes out. All right, so that's the differential equation. Okay, let's write it clearly somewhere else. All right, so it's going to be dA over dt. Inflow is 0 minus it's 5a over 200. That's simple. So we can really simplify it furthermore. So this is going to be dA over dt. It's minus 5a over 200, right? Or you can say 5 divided by 200. When you cancel out, what you're gonna get 40, right? So it's negative a over 40, and the initial condition is a0 is 10. Let's solve this differential equation. Here we can use separation of variables easily. dA over A, we can take that A to the left and keep negative 1 over 40 on the right. Take dt to the right, integrate. So if you integrate, you're going to get natural log absolute value of A. If you integrate negative 1 over 40, it's t over 40 plus c, arbitrary constant. Now to make A subject, or to get rid of ln, let's take the e of the right. So it's e to the negative t over 40 plus c. Right, so now we can furthermore, we can split that plus c in the exponent and we can write as e to the negative t over 40 times e to the c, right? E to the c an arbitrary constant, so it's c e to the negative t over 40. That's the solution of the differential equation. Now we can use the initial condition. So let's see, initially we have 10 grams. So we have 10 grams initially, c times t is 0, so c is 10, right? Okay, so A is going to be then 10 times e to the negative t over 40. That's the final solution of the differential equation. Okay, so that's how you set up the differential equation for problem 4 and solve it. Okay, now let's solve the third problem in the handout. Now this one is a tricky one. A tank initially contains 10,000 liters, so that's the volume, 10,000 liters. Okay, 10,000, that's big amount of water in liters of brine with salt concentration of 100 kilograms of salt. So you have 100 kilograms of salt, so it shouldn't be the concentration here, salt amount of 100 kilogram. Okay, so that's a typo because concentration should be kilogram over liter. So that's brine with a salt amount of 100 kilogram of salt. So that's what you have right now. So that's the initial amount of salt you have. That's why the units are very important. Okay, all right. Brine with 2 kilogram salt per 100 liters enters the tank. Okay, now let's set up the differential equation d over dt. So inflow information, first the concentration, brine with 2 kilograms per 100 liters. So 2 kilogram per 100 liters means, well, the concentration should be kilograms per liter, right? But here we have kilograms per 100 liters. So how many kilograms that comes in per liter? Well, you have to divide by 100, right? So really 0.02 kilograms per liter comes in to the tank. Okay, salt comes into the tank. So that's the concentration of salt that comes into the tank. So understand again, here we had 2 kilograms per 100 liters, but we need to find kilogram per 1 liter, not for 100 liters. So we divide by 100. So that's the concentration. Enters the tank at a rate of 20 liters per second. Okay, now you can see cancel out, that's good. And minus the outflow is, well, the outflow we don't know, amount divide by, well, 10,000, okay, and times the rate is the mixture leave at the same rate. So it's the rate is going to be, I'm struggling with the space, so it's 20 liters per second. So that's the rate. Okay, all right, let's make some space here and write the differential equation. So 20 times 0.02 is, if you multiply, it's going to be, I think, 0.4 if I'm correct. Let's see. Yes, minus here 0 and cancel out, 2 over 1000, it's a over 500. So I did some simplification. Let's write the differential equation again somewhere else so that we can see clearly. So it's dA over dt is equal to 0.4 minus a divided by 500. So that's the differential equation, and initial condition is a0 is 100. Great, let's solve it. Okay, so let me use separation of variables really here. Okay, so you have to make the common denominator. So 0.4 times 500 divided by 0.4 times 500 minus a over 500. Before we separate, we have to do this, otherwise we cannot separate algebraically, we cannot do it correctly. So 0.4 times 500 is actually 200 if I am correct. 4 times 500 is 2000. Yes, it's 200 minus a over 500. So that's what we get. Okay, as the common denominator. So let's separate the variables. So dA over 200 minus a and 1 over 500 dt. Now what we have to do is we have to integrate both sides. So if we integrate right hand side, it's t over 500 plus c, and if you integrate left hand side, it's natural log absolute value of 200 minus a divided by negative 1. Remember, you have to divide by the coefficient of a, which is negative 1. So let's take negative 1 to the right. So that's negative t over 500. Negative c is plus c, doesn't matter, it's c is an arbitrary constant. So to get rid of natural log, let's take the e of e to the negative t over 500 plus c. I hope now you are comfortable with this e to the c thing. So e to the c is an arbitrary constant, so it's c times e to the negative t over 500, 200 minus a. So then a can be written as the subject, 200 minus c e to the negative t over 500. That's the solution of the differential equation. Now let's use the initial condition. A0 is 100. So a is 100 when time is 0 minus c e to the 0 is 1, right? So c is what? 100. So the solution is a is equal to 200 minus c is 100 e to the negative t over 500. That's the solution of the differential equation. Okay, all right, so we've solved problem 2, 3 and 4 in this video. In the next video, I'm going to solve question 5 and 6 in the handout. Actually, we only need to set up the differential equation in 5 and 6. 5 and 6 is very different. You have to watch that video as well. Okay, so I'll catch you there hopefully.